Right now, as you listen to this, you are surrounded by warmth. The air around you is alive with motion. Invisible molecules of nitrogen and oxygen move at hundreds of meters per second, colliding with your skin billions of times every second. Each tiny impact transfers a microscopic amount of energy. The walls of the room around you quietly radiate infrared heat. The ground beneath you stores warmth absorbed earlier in the day. Even your own body is producing heat continuously, the byproduct of trillions of chemical reactions taking place inside living cells. To you, this feels completely normal. Warmth is so ordinary, so constant in our everyday experience, that we rarely stop to think about it. But step outside the fragile bubble of Earth's atmosphere, rise above the clouds, past the thin blue halo that protects this planet, and the universe becomes a profoundly different place. Out there, warmth is not the rule. Warmth is the exception. Because the truth about space is not simply that it is cold. The truth is far stranger. Most people imagine space as a kind of cosmic winter, a frozen void filled with biting cold, where anything exposed instantly turns to ice. Movies reinforce this idea. Science fiction often shows astronauts flash freezing the moment they drift outside their spacecraft. It is a powerful image, but it is wrong. Space is not cold in the way we understand cold. There is no freezing wind howling through the vacuum, no icy air stealing the warmth from your skin, no blizzard of frozen particles rushing past your body. In fact, there is almost nothing there at all. The vast darkness between the stars is not filled with cold air. It is filled with emptiness. In the deepest regions of interstellar space, a cubic centimeter of volume may contain only a single atom, sometimes even less. To appreciate how empty that is, compare it to the air you are breathing right now. That same tiny volume of air on Earth contains roughly 25 billion molecules. 25 billion. It is a number so large it barely makes sense in ordinary language, and yet in space, that swarm of particles disappears almost entirely. What remains is a vacuum so extreme that even the best laboratories on Earth struggle to reproduce it. And still, scientists often say that the temperature of the universe is about 2.7 Kelvin. That number sounds abstract, but it translates to a temperature of roughly minus 270 degrees Celsius, or minus 454 degrees Fahrenheit, just a few degrees above the coldest temperature that physics allows. If you heard that number without context, you might imagine that space must instantly freeze anything exposed to it, a place so brutally cold that survival would be impossible even for a moment. But here is the strange part. If a human were suddenly exposed to the vacuum of space, freezing would not happen instantly. In fact, the greater danger in many situations would be something completely different: overheating. Astronauts performing spacewalks outside the International Space Station must wear suits equipped with elaborate cooling systems. Inside those suits, chilled water circulates through a network of narrow tubes woven through the astronauts' clothing. This liquid cooling system continuously removes excess body heat and carries it away from the body. Without that cooling system, an astronaut could become dangerously overheated. At first glance, that seems impossible. How could anyone overheat in a place colder than nearly anywhere in existence? The answer reveals something deeply counterintuitive about the nature of temperature itself. Because the cold of space is not an active force. It does not rush toward you. It does not attack. It does not try to freeze you. Instead, the cold of space is something far stranger. It is the absence of almost everything. No air, no water, no dense clouds of gas, no atmosphere to press against your skin and pull heat away from your body. On Earth, when you step outside on a cold winter night, the air itself steals your warmth. Molecules in the atmosphere collide with your skin and carry away tiny amounts of energy with every impact. Wind accelerates this process by constantly replacing warmed air with colder air. This is why wind chill makes winter temperatures feel even colder than the thermometer suggests. But remove the air entirely. Remove every molecule of gas for millions of kilometers in every direction. Now imagine floating in that emptiness. Nothing touches your skin. Nothing collides with you. Nothing surrounds you that can conduct heat away through contact. Suddenly, the idea of temperature becomes much more complicated. Because temperature, in the strict scientific sense, is not a property of empty space. Temperature describes the motion of particles. It measures how fast atoms and molecules are moving. Hotter substances contain particles moving more rapidly. Cooler substances contain particles moving more slowly. But if there are almost no particles present at all, what exactly does temperature mean? In the vacuum between stars, the concept becomes strangely abstract. There is no ocean of cold air surrounding you. There is no icy environment trying to drag your body down toward absolute zero. Instead, there is something closer to perfect indifference. Space does not cool you. It simply allows your heat to escape. Every object that has a temperature above absolute zero radiates energy away in the form of electromagnetic radiation. Your body does this constantly. Even in a dark room, you are glowing faintly in infrared light, invisible to your eyes but easily detected by thermal cameras. The walls around you radiate heat as well. The air radiates heat. Everything warmer than absolute zero emits radiation continuously. Here on Earth, those flows of radiation are balanced by other forms of heat transfer. The air around you carries energy back and forth. Surfaces exchange warmth through conduction. The atmosphere acts like a vast thermal blanket that smooths out extreme temperature differences. But in space, two of the three major ways heat moves simply vanish. No conduction, no convection. Only radiation remains. And radiation is slow. Compared to the violent energy exchange happening inside Earth's atmosphere, the loss of heat through radiation alone is almost gentle. Your body would still lose energy in space, but not in the dramatic way most people imagine. You would not instantly freeze solid. Instead, your warmth would gradually radiate away into the darkness, photon by photon. The cold of space is not an assault. It is abandonment. It is the universe stepping aside and leaving you alone with your own heat. That subtle difference changes everything about how temperature works beyond Earth. It means that objects in space are not defined by the temperature of their surroundings. Instead, their temperature is determined by a balance between incoming and outgoing radiation, what shines on them, and what they emit. Consider an astronaut floating outside the International Space Station. On the side facing the sun, intense solar radiation pours in continuously. The sun delivers about 1,360 watts of energy per square meter at Earth's orbit. That is roughly equivalent to pressing a small space heater against every square meter of the astronaut's suit. Under direct sunlight, surfaces in orbit can reach temperatures exceeding 120 degrees Celsius. Hot enough to boil water. Hot enough to cause severe burns if protective systems failed. Yet just centimeters away, on the shadowed side of the same astronaut's body, the situation reverses dramatically. In shadow, with no sunlight arriving, and energy constantly radiating outward into the vacuum, temperatures can plunge below -150 degrees Celsius. Two extreme temperatures, separated by the width of a human body. Not because space has two different temperatures, but because radiation conditions change instantly across the boundary between light and shadow. This is the true thermal nature of space, not uniformly cold, but wildly extreme. One side burning, the other freezing, and the vacuum itself remaining almost completely indifferent to both. Before we continue deeper into this strange reality, take a moment to settle in. If the mysteries of the cosmos fascinate you, the silent depths of space, the hidden physics that shape the universe, and the strange truths that challenge everything we think we know, consider subscribing to Cosmos Before Us. This channel is where we explore the universe slowly, thoughtfully, and sometimes quietly enough to fall asleep to. And if the cosmos keeps you wondering, subscribe to Cosmos Before Us, and let the universe guide you to sleep. Now make yourself comfortable, because to truly understand how cold space is, we first need to understand something even more fundamental: what the word cold actually means. To understand why space behaves so strangely, we first have to confront a simple idea that almost everyone gets wrong. Cold is not actually a thing. It feels like a thing. It feels sharp, biting, physical. Step outside on a winter night and the cold seems almost alive. It creeps through your clothes, stiffens your fingers, reddens your skin, and makes the air sting as you breathe. But what you are feeling in those moments is not cold itself. You are feeling heat leaving your body. This may sound like a subtle difference, but it is one of the most important distinctions in all of physics. Because once you understand it, the mystery of space begins to make much more sense. Temperature is not the presence of coldness. It is a measure of energy. More specifically, temperature measures the average kinetic energy of particles, the motion of atoms and molecules that make up matter. When something is hot, the particles inside it are moving rapidly. They vibrate, collide, and bounce around with high energy. When something is cold, those same particles move more slowly. That is all temperature really describes: motion. The faster the particles move, the hotter the object appears. The slower they move, the colder it becomes. Absolute zero, the coldest possible temperature allowed by physics, is the point at which all molecular motion theoretically stops. At that temperature, atoms would sit perfectly still, holding the lowest possible amount of energy they can possess. But reaching absolute zero exactly is impossible. The laws of thermodynamics forbid it. Scientists have managed to cool atoms to fractions of a degree above absolute zero inside laboratories using elaborate equipment, lasers, and magnetic traps. Yet even the most advanced cryogenic experiments never quite reach the final boundary. There is always a tiny trace of motion left. Now here is where things become interesting. When you say that something feels cold, you are not measuring its temperature directly. Your body is measuring energy transfer. Imagine touching a metal railing outside on a chilly morning. The metal feels freezing to the touch, much colder than the wooden handle of a nearby door, even if both objects have been sitting in the same environment all night. The thermometer would show they are the same temperature. Yet your hand insists that the metal is colder. Why? Because metal conducts heat extremely well. The moment your skin touches the surface, heat from your body begins flowing rapidly into the metal. Energy leaves your hand faster than your body can replace it, and your nerves interpret that rapid loss of heat as cold. Wood, on the other hand, is a poor conductor. Heat leaves your skin much more slowly, so it does not feel nearly as cold, even though both objects share the same temperature. The sensation of cold, then, is not simply about temperature. It is about how quickly heat leaves your body. Your nervous system evolved to detect that loss of energy because maintaining a stable internal temperature is critical for survival. The human body works hard to stay around 37 degrees Celsius. Even small deviations from that range can interfere with biological processes. So whenever heat begins flowing out of your body too quickly, your brain interprets it as danger. Cold. This is why wind makes winter weather feel so much harsher. Moving air constantly replaces the thin layer of warmer air that surrounds your body. That protective layer normally acts as a small buffer, slowing the loss of heat from your skin. But when wind blows across your body, that layer disappears. Fresh, cold air takes its place. Heat leaves your body faster, and suddenly the temperature feels far lower than the thermometer indicates. Meteorologists even created a special measurement to describe this effect: wind chill. The faster the wind moves, the faster your body loses heat. Now imagine removing the air entirely. No wind, no molecules, no atmosphere of any kind. That is the environment of space. At first glance, you might expect this to make space unimaginably cold. After all, if cold weather happens when heat leaves your body quickly, then an environment without any warmth at all should freeze you instantly. But this intuition turns out to be completely wrong. Because when you remove the air, you also remove the primary mechanism that steals heat from your body. Conduction disappears. Convection disappears. Only radiation remains. Radiation is the third way heat can move from one place to another. Unlike conduction and convection, Radiation does not require matter. It travels through empty space in the form of electromagnetic waves. Every object with a temperature above absolute zero emits radiation continuously. Your body does it. The walls around you do it. The earth does it. The sun does it on an enormous scale. But radiation is a relatively slow process compared to the violent energy exchange happening in air or water. When you stand outside on Earth, billions of air molecules slam into your skin every second, rapidly carrying heat away from your body. In space, nothing collides with you. Your body still radiates heat outward as infrared light, but the rate at which this happens is much slower than most people expect. This means the vacuum of space does not instantly freeze objects the way people imagine. Instead, objects gradually cool as they radiate energy away. The vacuum is not aggressively cold, it is simply empty. To make this clearer, imagine standing in a perfectly insulated room with no air inside. The walls are far away, and nothing touches your body. You would still lose heat slowly through radiation, but the process would feel very different from stepping outside into freezing wind. No biting chill, no icy gusts, just a slow, quiet leakage of warmth into the darkness. This is much closer to how space actually behaves. Which brings us back to the strange paradox we mentioned earlier. If space does not rapidly steal heat from your body, why are astronauts so concerned about temperature control? Why do spacecraft need massive radiator panels? Why do spacesuits contain elaborate cooling systems? The answer lies in a third, often overlooked truth about temperature. Cold environments are not always the most dangerous ones. Sometimes the greatest threat comes from heat that has nowhere to go. On Earth, heat escapes easily. The air around us carries energy away through convection. Wind transports warmth from one place to another. Oceans move enormous amounts of thermal energy across the planet. Our atmosphere acts like a gigantic heat redistribution system. In space, none of that exists. Once heat builds up inside an object, it has only one way to escape: radiation. And radiation, as we have seen, is slow. This is why spacecraft designers spend enormous effort controlling temperature. Electronic systems inside satellites generate heat continuously. Computers, batteries, and instruments all produce energy as they operate. If that heat cannot escape fast enough, the entire spacecraft could overheat. So instead of worrying only about freezing, engineers must carefully balance both sides of the thermal equation. Too much heat entering, too little heat leaving. Too little heat entering, too much heat leaving. The delicate balance between these two processes determines the temperature of every object in space. And once we understand that balance, we are ready to explore the next piece of the puzzle. Because the vacuum of space does not simply change how heat moves, it eliminates two of the three mechanisms entirely, leaving behind only one: radiation. And that single remaining pathway is the key to understanding how temperature truly works beyond Earth. To truly understand how temperature behaves in space, we now need to look at the three fundamental ways heat moves through the universe. On Earth, heat is constantly flowing from place to place. Energy moves through the air, through water, through solid objects, and even through empty space. These flows happen so naturally that we rarely stop to think about them. But all heat transfer falls into just three categories. Three physical processes that govern how energy travels from one object to another: conduction, convection, and radiation. Every temperature change you have ever experienced in your life involves one or more of these three mechanisms working together. Here on Earth, they operate simultaneously almost everywhere. They blend together so seamlessly that it can be difficult to separate them in your mind. But space removes two of them entirely. And once those two disappear, the nature of temperature changes in ways that seem almost alien. Let's start with the most familiar mechanism: conduction. Conduction is the transfer of heat through direct contact between materials. It happens when faster-moving particles collide with slower-moving ones, passing energy along through a chain of interactions. Imagine placing your hand on a hot stove. The metal surface contains atoms vibrating rapidly with thermal energy. When your skin touches the metal, those energetic atoms collide with the atoms in your hand. Energy flows from the hotter object into the cooler one. You feel heat. The same thing happens in reverse when you touch something cold. If you place your bare hand against a block of ice, the atoms in your skin are vibrating more quickly than those in the ice. Energy flows outward from your body into the frozen surface. Your skin loses heat rapidly, and your nerves interpret that loss as cold. This is conduction in action. It is the reason metal objects feel colder than wooden ones in winter. Metal conducts heat efficiently, allowing energy to flow quickly from your body into the object. Wood is a poor conductor, so the same temperature surface feels much warmer. Conduction requires something essential: matter. There must be atoms and molecules physically touching each other so they can exchange energy through collisions. Now imagine removing the air. Remove every molecule between you and the object you are touching. Suddenly, conduction becomes impossible. There are no particles to carry the energy. In the vacuum of space, conduction almost completely disappears. Unless two solid objects are physically touching, there is no pathway for conduction to occur. The second mechanism of heat transfer is convection. Convection happens when heat is carried by the motion of fluids, liquids or gases that flow from place to place. On Earth, convection is everywhere. Warm air rises because heated gases expand and become less dense. Cooler air sinks because it is denser. This movement creates circulation patterns that transport heat throughout the atmosphere. Weather itself is driven largely by convection. Rising warm air forms clouds. Sinking cool air creates high-pressure systems. Ocean currents transport enormous quantities of heat across the surface of the planet. Even something as simple as a pot of boiling water on a stove demonstrates convection beautifully. Water at the bottom of the pot absorbs heat from the burner. As it warms, it becomes less dense and rises toward the surface. Cooler water sinks to replace it. The result is a continuous circulation pattern that distributes heat throughout the entire pot. Convection is an incredibly efficient way to move energy. But like conduction, it requires matter. Specifically, it requires a fluid medium, air, water, or some other substance capable of flowing. Now imagine removing the fluid. Remove the atmosphere. Remove the oceans. Remove every gas molecule capable of rising or sinking. In space, there is nothing to circulate. No air currents, no flowing liquids, no convection cells. Without a medium to carry heat from one place to another, convection disappears completely. This leaves us with only the third mechanism: radiation. Radiation is the transfer of energy through electromagnetic waves. Unlike conduction and convection, radiation does not require matter at all. Energy can travel through empty space as oscillating electric and magnetic fields moving at the speed of light. The most familiar example of radiation is sunlight. The sun is nearly 150 million kilometers away from Earth. Between us lies the vacuum of space. No air connects the two worlds, yet energy from the sun streams toward Earth continuously. Those photons travel across empty space, carrying warmth with them. When they strike Earth's surface, they deposit energy that heats the land, the oceans, and the atmosphere. Without radiation, our planet would be a frozen world. Radiation is also happening everywhere around you right now. Every object with a temperature above absolute zero emits electromagnetic radiation continuously. Your body radiates infrared light. The floor beneath you radiates heat. Even the walls of your room are quietly glowing in wavelengths your eyes cannot see. At everyday temperatures, most radiation occurs in the infrared part of the electromagnetic spectrum. But as temperatures rise, the wavelength of emitted radiation becomes shorter and more energetic. This is why extremely hot objects begin to glow visibly. A metal rod heated in a furnace first glows dull red. As its temperature rises, the glow becomes brighter and shifts toward orange, then yellow, then white. At even higher temperatures, the radiation moves into the ultraviolet part of the spectrum. Stars are simply enormous objects emitting radiation at extremely high temperatures. The surface of our sun, for example, sits at about 5,500 degrees Celsius. At that temperature, It emits intense radiation across a wide range of wavelengths, including visible light. That radiation spreads outward in every direction, crossing millions of kilometers of empty space. Eventually, a tiny fraction of those photons reach Earth, and that tiny fraction is enough to power the entire climate system of our planet. Now we arrive at the crucial insight about space. In the vacuum beyond Earth's atmosphere, only one of these three heat transfer mechanisms survives. Conduction disappears. Convection disappears. Radiation remains. This changes everything. On Earth, if something becomes hot, the surrounding air quickly carries heat away through convection. Wind disperses energy, water evaporates and removes heat from surfaces. Thermal gradients smooth out quickly because fluids constantly move energy around. But in space, there is no atmosphere to act as a thermal buffer. Energy cannot be transported away through air currents. Heat cannot be conducted away through a surrounding medium. Instead, objects must rely entirely on radiation to lose energy. And radiation, compared to conduction and convection, is slow. This is why spacecraft engineers must carefully design systems to manage temperature. Electronic components inside satellites generate heat continuously. Computers, sensors, and batteries all convert electrical energy into thermal energy during operation. If that heat cannot escape quickly enough, the spacecraft could overheat even while surrounded by the cold vacuum of space. To prevent this, spacecraft often include large radiator panels, flat surfaces designed specifically to emit infrared radiation efficiently. These radiators face away from the sun and glow quietly in wavelengths invisible to human eyes, shedding excess heat into the darkness. At the same time, other parts of the spacecraft must be insulated to prevent them from becoming too cold. In orbit, temperatures can swing wildly depending on whether a surface faces the sun or lies in shadow. A satellite may spend half of its orbit bathed in intense sunlight, absorbing large amounts of energy. Then minutes later it plunges into darkness, where its surfaces begin radiating heat away into the vacuum. These rapid thermal cycles create one of the greatest engineering challenges in spaceflight. Maintaining thermal balance. Too much radiation absorbed. Too little radiation emitted. Too little energy coming in. Too much energy leaving. Every spacecraft constantly walks this narrow line, and astronauts themselves must do the same. Spacesuits are not simply protective shells that keep astronauts warm. They are sophisticated thermal regulation systems. Inside a modern spacesuit, a network of tubes circulates chilled water around the astronaut's body. This liquid cooling garment absorbs excess body heat and carries it away, preventing overheating during spacewalks. Without that system, the astronaut's own metabolism, combined with absorbed solar radiation, could raise internal temperatures to dangerous levels. This is the strange paradox of space. An environment often described as unimaginably cold can still threaten objects with dangerous overheating. Because in space, temperature is not determined by the environment alone. It is determined by a balance. Energy coming in, energy going out. Radiation absorbed, radiation emitted. And once we understand that balance, we can finally return to the number that started this journey. The famous claim that the temperature of the universe is about 2.7 Kelvin, a number so cold it sits just a few degrees above absolute zero. But where does that number come from? And what does it actually mean? To answer that question, we must travel far beyond the mechanics of heat transfer and look instead at the oldest light in the universe itself. Now that we understand the three ways heat moves, conduction, convection, and radiation, we can finally look at how temperature actually behaves in space. And the first thing to understand is this. Space does not have a single temperature. That idea alone can feel surprising. On Earth, temperature usually behaves in a fairly predictable way. The air in a room might be 20 degrees Celsius. The water in a lake might be 10 degrees. The air on a winter night might drop below freezing. We imagine environments having a temperature in the same way we imagine objects having weight or color. But the vacuum of space does not behave like an environment filled with air. There is no medium surrounding objects to impose a shared temperature. Instead, every object in space largely determines its own temperature based on one simple equation: how much radiation it absorbs versus how much radiation it emits. If an object absorbs more energy than it radiates away, it warms up. If it radiates away more energy than it absorbs, it cools down. That balance alone determines its temperature. The vacuum surrounding it plays almost no direct role. This leads to one of the most extreme thermal environments anywhere in the universe. Because in space, temperatures can swing wildly across distances as small as a few centimeters. To see how dramatic this can be, imagine an astronaut floating outside the International Space Station during a spacewalk. On the side of the astronaut's body facing the sun, an enormous stream of radiation pours in continuously. At Earth's distance from the sun, sunlight carries roughly 1,360 watts of energy per square meter. That is about the same amount of power produced by a small electric space heater. But in orbit, there is no atmosphere to filter or scatter that radiation. No clouds, no air molecules. Nothing stands between the sun and the astronaut except the thin layers of the spacesuit. The sunlight strikes the suit directly, delivering energy with relentless intensity. Under these conditions, the surface of the suit can climb above 120 degrees Celsius, hot enough to boil water, hot enough to cause severe burns if a human were exposed without protection. Now shift your attention just a little to the side of the astronaut facing away from the sun. Here, the situation is completely different. This side receives no direct sunlight. Instead, it is exposed only to the darkness of space. The surface continues radiating heat away in the form of infrared light, but very little radiation arrives to replace the lost energy. As a result, the temperature can plummet below -150 degrees Celsius. Two radically different temperatures, separated by the width of a human body. And neither of them truly represents the temperature of space. What you are seeing instead is the consequence of radiation balance. One side absorbs enormous amounts of energy from the sun. The other side radiates energy into the darkness. The vacuum itself simply allows both processes to happen without interference. This same principle explains the dramatic temperature swings found on the moon. Unlike Earth, the moon has almost no atmosphere. Without a blanket of air to redistribute heat, the lunar surface experiences some of the most extreme temperature variations in the solar system. During the long lunar day, which lasts about 2 Earth weeks, the sun shines continuously on the same region of the surface. With nothing to block or diffuse the sunlight, the ground absorbs radiation directly. Temperatures can climb to about 127 degrees Celsius, hotter than boiling water. But when the moon rotates into night, the situation reverses. For the next 2 weeks, that same patch of ground sits in complete darkness. No sunlight arrives. The surface continues radiating its heat into space, and with nothing replacing that lost energy, the temperature steadily falls. Eventually, it can drop to around -173 degrees Celsius, a temperature difference of roughly 300 degrees between day and night, and all of it caused by the absence of an atmosphere. On Earth, such extreme swings are impossible. Our atmosphere acts like a massive thermal regulator. Air circulates around the planet through convection currents, transporting heat from warm regions to cooler ones. Clouds reflect some incoming sunlight. Greenhouse gases trap some outgoing infrared radiation. All of these processes combine to smooth out temperature differences across the surface of the planet. Without that protective blanket, the environment becomes far more brutal. But the moon still has one advantage over empty space. Its surface stores heat. Solid rock and soil can absorb energy during the day and release it slowly at night. Even with no atmosphere, this thermal inertia moderates temperature changes slightly. A spacecraft drifting through deep space does not even have that advantage. Consider a small satellite orbiting Earth. Half of every orbit, the spacecraft sits in direct sunlight. Its surfaces absorb solar radiation and begin to warm. Then, as it passes behind Earth, the spacecraft enters shadow. The sunlight disappears instantly. And now the satellite begins radiating heat into space. Without incoming energy to replace what is lost, the temperature begins dropping rapidly. This cycle repeats every 90 minutes for satellites in low Earth orbit. Sunlight, shadow, heating, cooling over and over again. Each transition can create enormous stresses on materials. Metal expands when heated and contracts when cooled. Electronics operate best within narrow temperature ranges. Batteries and instruments can fail if they become too hot or too cold. This is why spacecraft are designed with complex thermal control systems. Engineers must carefully control which surfaces absorb sunlight and which surfaces radiate heat away. Some parts of the spacecraft are coated with reflective materials that bounce sunlight away. Others are designed to absorb heat intentionally. Radiator panels are positioned to face deep space, where they can emit infrared radiation efficiently. Even the orientation of the spacecraft may be adjusted during flight to regulate temperature. In some missions, spacecraft perform a slow rotation known as a thermal roll, sometimes nicknamed the barbecue roll. By rotating slowly, the spacecraft ensures that no single side faces the sun for too long. Heat spreads more evenly across the structure, preventing extreme temperature differences from building up. Without these precautions, the harsh thermal environment of space could destroy delicate instruments in a surprisingly short time. Yet, despite these dramatic extremes, scorching sunlight on one side, freezing darkness on the other, space itself still contributes almost nothing to the temperature of the objects drifting through it. The vacuum is not actively freezing them. It is simply allowing them to radiate energy away. And that distinction becomes even more important when we move far beyond the orbit of Earth. Out in the deep darkness between the stars, sunlight becomes incredibly weak. The nearest star to our Sun lies more than 4 light-years away. At such enormous distances, the radiation from other stars becomes so faint that it barely contributes any measurable warmth at all. Any object drifting through that interstellar darkness will slowly radiate away its internal heat. Year after year, century after century, gradually cooling. But it will never cool all the way to absolute zero. Because even in the deepest voids of space, there is still one faint source of energy present everywhere in the universe. A dim glow of ancient radiation left behind by the birth of the cosmos itself. That glow fills every direction of the sky. It bathes every galaxy, every star, every drifting grain of dust, and it sets the ultimate temperature floor of the universe. About 2.7 Kelvin. To understand where that number comes from, we must travel back almost 14 billion years, to a time when the entire universe was hotter than the core of any star that exists today. By now, the strange thermal reality of space should be starting to come into focus. Space itself does almost nothing. It does not warm you. It does not aggressively freeze you. It simply allows energy to move through radiation. That might sound harmless at first, but for engineers designing spacecraft, this indifference creates one of the most difficult challenges in all of spaceflight. Because in space, heat does not behave the way it does on Earth. On Earth, excess heat can escape easily. Air carries it away through convection. Wind spreads warmth across large areas. Water evaporates and removes energy from surfaces. Buildings release heat into the surrounding atmosphere. Our planet is full of natural cooling systems. In space, none of those systems exist. There is no air to carry heat away, no wind to disperse energy, no fluid to transport warmth from one place to another. Once heat builds up inside an object in space, the only way for that energy to leave is through radiation. And radiation, compared to convection or conduction, is slow. This single fact has shaped nearly every spacecraft ever built. Take the International Space Station, for example. From a distance, the ISS looks like a collection of modules, trusses, and solar panels floating quietly above Earth. But if you look more closely, you will notice enormous flat structures extending outward from the station. These are not solar panels. They are radiators. Massive thermal radiators designed specifically to dump heat into space. Inside the station, hundreds of systems are constantly generating energy. Computers process data. Science experiments run continuously. Electrical systems distribute power across the station. Even the astronauts themselves contribute heat through normal metabolism. Every electronic circuit produces waste heat as it operates. Without a way to remove that energy, the interior of the station would slowly warm, then continue warming, then warming further, until equipment began to fail. Eventually, the station itself could become uninhabitable. The solution is simple in principle, but difficult in practice. Radiate the heat away. The ISS circulates liquid coolant through pipes that collect heat from inside the station. That coolant flows outward toward the large radiator panels mounted on the station's exterior structure. There, the radiators release the heat as infrared radiation, glowing faintly into the darkness of space. Invisible to human eyes, but essential for survival. Those radiator wings span roughly 2,500 square feet of surface area. Without them, the space station would quickly overheat. But the challenge does not end there. While some parts of the station must lose heat, other parts must be carefully protected from becoming too cold. Remember, in shadow, objects in space can cool rapidly as they radiate energy away. Electronics, batteries, and mechanical systems often require stable temperatures to function properly. If they become too cold, materials contract, chemical reactions slow, and lubricants can freeze or thicken. So spacecraft designers must constantly balance two opposing threats: too hot, too cold. Some components require heaters to keep them within safe operating ranges. Other components require insulation to slow the loss of heat. Multi-layer insulation blankets, often recognizable as shiny gold or silver coverings, wrap around spacecraft surfaces like thermal armor. These blankets reflect radiation and reduce the rate at which energy flows into or out of the spacecraft. Even with all these protections, the orientation of the spacecraft itself becomes critical. If one side of a spacecraft faces the sun for too long, it can absorb enormous amounts of energy. Meanwhile, the opposite side may sit in deep shadow, radiating heat away and becoming dangerously cold. The temperature difference across the structure can become extreme, one side baking, the other freezing. To prevent this imbalance, spacecraft sometimes perform a slow rotation while traveling through space. Engineers call this maneuver passive thermal control, but astronauts have given it a far more colorful nickname: the barbecue roll. Imagine placing a piece of meat on a grill and slowly rotating it so that every side cooks evenly. Spacecraft do something very similar. By rotating slowly, sometimes only once every few minutes or hours, the spacecraft spreads sunlight evenly across its surfaces. No single side receives constant exposure to the sun. This simple motion helps maintain a more stable temperature across the entire structure. The barbecue roll was famously used during the Apollo missions to the moon. As the spacecraft traveled through deep space, mission controllers instructed the spacecraft to rotate slowly to prevent overheating on one side and excessive cooling on the other. Without this maneuver, the extreme thermal environment could have caused serious problems for the spacecraft systems. The same principle applies to satellites orbiting Earth today. In low Earth orbit, spacecraft pass into sunlight and shadow repeatedly as they circle the planet. Each transition can cause sudden temperature shifts. One moment, the spacecraft is bathed in solar radiation. Minutes later, it enters the darkness of Earth's shadow. Engineers design thermal control systems that can handle these constant cycles. Reflective coatings help reduce solar absorption. Radiators release excess heat. Insulation slows the loss of energy. Active heaters maintain minimum temperatures where necessary. Every mission must carefully account for these thermal conditions. Even the materials used to build spacecraft are chosen with temperature changes in mind. Metals expand when heated and contract when cooled. If temperature swings become too large, structural stresses can develop. Over time, repeated expansion and contraction can damage components. So engineers designed structures that can tolerate these changes, ensuring that thermal cycling does not tear spacecraft apart. The same concerns apply to astronauts during spacewalks. A modern spacesuit is not simply a protective shell. It is a highly sophisticated environmental control system. Inside the suit, astronauts wear a liquid cooling garment, a network of thin tubes running across their torso, arms, and legs. Chilled water flows through these tubes, absorbing excess heat from the astronaut's body. That warmed water then circulates through the suit's life support system, where the heat is removed and released into space through radiators. Without this cooling system, the astronaut's body heat combined with absorbed solar radiation could quickly raise temperatures to dangerous levels. Ironically, even while floating in an environment close to absolute zero, astronauts must worry about overheating. This perfectly illustrates the central paradox of space. The vacuum itself does not determine temperature. Radiation does. Where energy comes from, where energy goes. What objects absorb, what objects emit. Every spacecraft, every astronaut, every satellite must live within this delicate balance. And this balance becomes even more fascinating when we step away from individual spacecraft and begin looking at the universe itself. Because if space does not truly have a temperature in the usual sense, why do scientists say that the universe sits at 2.7 Kelvin? What is providing that faint warmth? And why does that number appear everywhere we look in the cosmos? To answer that, we have to look not at modern spacecraft, but at the oldest light in the universe, a faint glow that has been traveling through space for nearly 14 billion years. If you could travel far enough away from every star, every planet, and every galaxy, far beyond the glowing structures that light up our night sky, you would eventually find yourself in a region of space so dark and empty that almost nothing exists there at all. No nearby suns, no planets, no glowing nebulae. Just an immense stretch of intergalactic darkness. At first glance, it might seem that such a place should be perfectly cold. After all, if there are no stars nearby to provide warmth and no planets radiating heat, then surely the temperature there should drop all the way to absolute zero. But surprisingly, it never does. Even in the deepest voids of space, regions separated from the nearest galaxies by tens of millions of light years, there is still a faint background glow. It is incredibly weak, far too faint for human eyes to ever see. Yet it fills every direction of the sky. And it sets the lowest natural temperature that anything in the universe can reach. That temperature is 2.725 Kelvin, only a tiny fraction above absolute zero. To understand why this faint warmth exists everywhere in the cosmos, we must travel back nearly 14 billion years to the earliest moments in the history of the universe. At the beginning, the universe was nothing like the cold darkness we see today. In its first moments after the Big Bang, the universe was unimaginably hot. Temperatures were not merely thousands or millions of degrees. They were trillions. The entire cosmos existed as a dense, glowing plasma of particles and radiation. Matter and energy were packed together so tightly that atoms could not even exist yet. Electrons and atomic nuclei were constantly colliding with photons in a seething storm of energy. Light itself could not travel freely. Every photon that attempted to move through the universe would immediately collide with a charged particle and scatter in a new direction. The universe was opaque. Every direction was filled with a blinding fog of radiation. But the universe was also expanding. From the very beginning, space itself began stretching outward. As space expanded, the density of matter decreased. The temperature began to fall. Seconds passed, minutes, years, then hundreds of thousands of years. As the universe continued expanding, it gradually cooled enough for a remarkable event to occur. Electrons finally slowed down enough to combine with atomic nuclei. Hydrogen atoms formed for the first time. Helium atoms formed as well. This moment, known as recombination, happened roughly 380,000 years after the Big Bang. And when it happened, the universe suddenly became transparent. Without free electrons constantly scattering photons, light could finally travel freely through space. The fog lifted. Photons that had previously been trapped began streaming outward in every direction. That ancient light has been traveling ever since. across billions of years, across billions of light years of expanding space. And even today, those same photons are still arriving from every direction in the sky. This ancient radiation is what scientists call the cosmic microwave background, often abbreviated as the CMB. It is the oldest light we can observe in the universe, a fossil from the earliest era of cosmic history. When those photons were first released, the universe had cooled to roughly 3,000 Kelvin, about the temperature of the surface of a red-hot metal. At that time, the entire sky would have glowed a dim orange-red color. If any observer had existed then, the universe would not have appeared dark at all. It would have looked like a glowing fog stretching endlessly in every direction. But the universe continued expanding, and as space expands, something strange happens to light traveling through it. The light waves stretch. Imagine drawing waves on the surface of a balloon. As the balloon inflates, the waves become longer and longer. The same thing happens to photons traveling through expanding space. Their wavelengths stretch over time. As the wavelength increases, the energy of the photon decreases. And as the energy decreases, the temperature associated with that radiation drops. Over billions of years, the light released during recombination has been stretched dramatically. Originally, those photons were part of the visible spectrum. But today, their wavelengths have grown more than 1,000 times longer. They now fall into the microwave region of the electromagnetic spectrum, hence the name, cosmic microwave background. What was once visible light glowing at 3,000 Kelvin has cooled dramatically as the universe expanded. Today, the temperature of that radiation corresponds to just 2.725 Kelvin. And because that radiation fills the entire universe, it effectively sets a temperature floor. Any object drifting through deep space, far from stars or galaxies, will eventually cool until it reaches thermal equilibrium with this background radiation. At that point, it will absorb as much energy from the cosmic microwave background as it emits through its own radiation. Its temperature stabilizes, about 2.7 Kelvin. This means the universe itself carries a faint memory of its hot beginnings. Every direction in the sky contains photons that have been traveling since the universe was less than 500,000 years old. Every cubic centimeter of space contains roughly 400 of these ancient photons. They are everywhere, passing through you, passing through Earth, passing through entire galaxies. You do not see them. You do not feel them. But they are there. The discovery of this radiation in 1964 became one of the most important moments in modern cosmology. Two radio astronomers, Arno Penzias and Robert Wilson, were working with a large microwave antenna in New Jersey. They were attempting to eliminate noise in their radio receiver so they could perform sensitive astronomical measurements. But no matter what they did, a faint background signal remained. They cleaned the antenna. They accounted for interference from cities. They even removed pigeon droppings from the equipment. Yet the signal persisted. It appeared to come from every direction in the sky equally. Eventually, they realized that the mysterious noise was not coming from Earth at all. It was coming from the universe itself. They had accidentally discovered the cosmic microwave background, the faint thermal echo of the Big Bang. This discovery provided one of the strongest pieces of evidence that the universe began in a hot, dense state and has been expanding and cooling ever since. Later satellite missions, such as COBE, WMAP, and Planck, mapped this radiation across the entire sky with incredible precision. Their measurements showed that the temperature of the cosmic microwave background is almost perfectly uniform. Every direction in the universe has nearly the same temperature. Only tiny variations exist, differences of about 1 part in 100,000. These minute fluctuations are incredibly important. They represent the earliest seeds of structure in the universe. Slightly denser regions of matter eventually collapsed under gravity to form galaxies, stars, and planets. In a sense, every galaxy we see today began as a tiny ripple in the temperature pattern of the cosmic microwave background. But for our story about temperature, the most important fact is this. The cosmic microwave background fills the universe. Everywhere. Even in the emptiest voids between galaxies. Which means that no object in the universe can cool below that temperature naturally. If a rock were drifting through deep intergalactic space for billions of years, it would slowly radiate away its internal heat, gradually cooling, year after year. But eventually it would reach equilibrium with the background radiation. And it would stop cooling further. About 2.7 Kelvin. This faint glow, the afterimage of the Big Bang, acts like the universe's minimum thermostat. It prevents the cosmos from ever reaching true absolute zero. Yet even this tiny warmth is incredibly weak. Compared to the radiation from stars, the cosmic microwave background contributes almost nothing. Near the Earth, sunlight delivers millions of times more energy than the CMB. Even in deep space, the background radiation is so faint that it barely warms anything. And because of that, something fascinating happens. In a few extremely rare places in the universe, natural processes can actually produce temperatures even lower than the cosmic microwave background itself. For a brief moment, certain objects can become colder than the universe. And one of those places holds the record for the coldest known natural temperature anywhere in existence. A strange and beautiful cloud of gas known as the Boomerang Nebula. A place so cold that it challenges the very limits of cosmic temperature. And to understand how such a thing is possible, we must travel next to the outer edges of a dying star, where expanding gas is cooling faster than the universe itself. For almost the entire universe, the temperature floor is set by the faint glow of the cosmic microwave background, about 2.7 Kelvin. That number appears everywhere. It fills the sky in every direction. Any lonely object drifting through deep space will eventually cool until it reaches that temperature and no lower. In most places, that is the end of the story. But the universe occasionally produces strange exceptions. There exists a place where nature has managed to create temperatures even colder than the background radiation of the cosmos itself. A place where gas cools so efficiently that it drops below the natural temperature floor of the universe. It is called the Boomerang Nebula, and it may be the coldest natural environment ever discovered. The Boomerang Nebula lies roughly 5,000 light-years from Earth, in the direction of the constellation Centaurus. At first glance, it does not appear particularly remarkable. When astronomers first observed it with optical telescopes, it looked like a faint cloud of gas surrounding a dying star. But as more powerful instruments began studying the object in greater detail, something extraordinary became clear. This nebula was unbelievably cold. Not just colder than most nebulae, colder than the cosmic microwave background itself. Measurements revealed temperatures as low as 1 Kelvin, just 1 degree above absolute zero. To appreciate how extreme that is, remember what we learned earlier. Even the deepest voids of intergalactic space hover around 2.7 Kelvin because they are bathed in the faint radiation left over from the Big Bang. Yet somehow this expanding cloud of gas had cooled to less than half that temperature. It was colder than the universe surrounding it. How is that possible? The answer lies in the physics of expansion. At the center of the Boomerang Nebula sits a dying star, a red giant nearing the final stages of its life. Like many aging stars, it has begun shedding its outer layers into space. Vast quantities of gas are being ejected outward at enormous speeds. But this is not a gentle stellar breeze. The gas is blasting outward in a powerful flow moving roughly 160 kilometers per second. As this gas expands rapidly into space, something remarkable happens. It cools. This phenomenon is known as adiabatic cooling. You have experienced a version of this effect many times without realizing it. If you spray an aerosol can or release compressed gas from a container, the escaping gas becomes noticeably cold. The reason is simple. When gas expands rapidly, its particles spread out and lose energy. Their motion slows, and as their motion slows, the temperature drops. Inside the Boomerang Nebula, this effect is happening on an enormous cosmic scale. The star at the center is ejecting gas so quickly that the expanding cloud cools faster than it can absorb radiation from the surrounding universe. In other words, the gas loses energy faster than the cosmic microwave background can warm it. For a brief time in cosmic terms, the nebula becomes colder than the universe itself. Astronomers studying the Boomerang Nebula with radio telescopes detected this extreme temperature through its interaction with the cosmic microwave background. Instead of simply emitting radiation like most nebulae, the Boomerang Nebula actually absorbs radiation from the background. It appears as a dark silhouette against the faint microwave glow of the universe. This absorption revealed just how cold the gas had become. About 1 Kelvin. For comparison, that is colder than most of the cryogenic temperatures routinely used in laboratories on Earth. Liquid nitrogen boils at 77 Kelvin. Liquid helium boils at about 4 Kelvin. The Boomerang Nebula is colder than both. In fact, it is so cold that it approaches temperatures normally achievable only with advanced scientific equipment. Yet nature produced it spontaneously. But even the Boomerang Nebula cannot remain colder than the universe forever. Eventually, the expanding gas will slow. The nebula will disperse into interstellar space, and as it spreads outward, the cosmic microwave background will gradually warm the gas until it once again approaches the universal baseline of 2.7 Kelvin. The coldest place in the universe will slowly fade back toward the cosmic average. The Boomerang Nebula is therefore not a permanent record holder. It is a temporary phenomenon. A fleeting moment where the physics of expansion briefly pushes matter below the background temperature of the cosmos. Yet its existence reveals something important. Even the faint glow of the Big Bang does not dominate every corner of space equally. Under the right conditions, matter can momentarily escape the thermal influence of the universe itself. But these cases are extraordinarily rare. For the overwhelming majority of space, the cosmic microwave background remains the ultimate temperature floor. And that leads us to a much larger realization. The warm places in the universe, the stars, planets, and glowing nebulae, are actually the exception, not the rule. Because when we zoom out far enough, the cosmos reveals a startling truth. Nearly all of its volume is filled with darkness hovering just a few degrees above absolute zero. The hot regions we see through telescopes are tiny islands of warmth scattered across an ocean of cold. And once we begin measuring the scale of the universe, that imbalance becomes almost impossible to comprehend, because the stars that seem so bright in our night sky occupy an almost unimaginably small fraction of the total space that exists. To see how dramatic that imbalance really is, we now need to step back and look at the architecture of the universe itself. The vast structure of galaxies, cosmic voids, and the immense cold emptiness that lies between them. If you step outside on a clear night and look up at the sky, it is easy to believe that the universe is full of light. Thousands of stars scatter across the darkness. The Milky Way stretches like a glowing river overhead. Through a telescope, countless galaxies appear, spirals, clusters, and glowing clouds of gas spread across the cosmos. At first glance, the universe seems busy, bright, almost crowded. But this impression is deeply misleading. The truth is that nearly everything in the universe is cold, dark, and empty. The luminous objects we see, the stars, the nebulae, the galaxies, are the rare exceptions. They stand out precisely because they are surrounded by such enormous volumes of darkness. To understand how extreme this imbalance really is, imagine shrinking the sun to the size of a ping-pong ball. If the sun were that small, Earth would be a tiny grain of sand orbiting roughly 2.5 meters away. Already the scale feels enormous. But the nearest star to the sun, Proxima Centauri, would not be sitting somewhere across the room. It would be another ping-pong ball placed roughly 700 miles away. Between those two tiny spheres lies almost nothing. Hundreds of miles of empty tabletop. Two small islands of warmth separated by an immense gulf of darkness. And this is not unusual spacing, it is typical. In our region of the Milky Way galaxy, the average distance between stars is roughly 4 light-years. That means light itself, traveling at nearly 300,000 kilometers per second, takes more than 4 years to cross the gap between neighboring stars. For comparison, sunlight reaches Earth in just 8 minutes. But between stars, distances are measured not in minutes or hours or days. They are measured in years. And the space between them is almost completely empty. A few atoms drift through the darkness. Occasionally, a stray dust particle passes by. But the density of matter is so low that a cubic centimeter of interstellar space may contain only 1 or 2 particles. That is not a typo, 1 or 2. Compare that to the billions of molecules packed into the same volume of air on Earth. When astronomers describe space as a vacuum, they are not exaggerating. The emptiness is almost total. Now zoom out even farther. Instead of looking at stars, look at entire galaxies. Our Milky Way galaxy contains hundreds of billions of stars. It stretches roughly 100,000 light-years across, forming a vast spiral of glowing stellar systems. Yet even galaxies are separated by enormous distances. The nearest large galaxy to us, the Andromeda Galaxy, sits about 2.5 million light-years away. That distance is so immense that if the Milky Way were shrunk to the size of a dinner plate, Andromeda would be another plate placed nearly 2 miles away. Between them, almost nothing, just cold, empty space. But the structure of the universe becomes even more astonishing when astronomers map the distribution of galaxies across the largest cosmic scales. Galaxies do not fill the universe evenly. Instead, they form vast networks of filaments and clusters, enormous strands of matter stretching across hundreds of millions of light-years. These structures form what scientists call the cosmic web. Imagine an immense 3-dimensional spiderweb stretching across the observable universe. The threads of the web contain galaxies and galaxy clusters, but the spaces between the threads are enormous. These regions are called cosmic voids, and they are truly gigantic. A typical cosmic void may span 100 to 300 million light-years across. Inside these regions, galaxies are extremely rare. In some cases, astronomers can search vast volumes of space and find only a handful of small galaxies scattered across distances that dwarf entire clusters elsewhere. Most of the universe's volume lies inside these voids. Estimates suggest that roughly 80 to 90% of the observable universe consists of these enormous empty regions. This means that if you could randomly choose a point anywhere in the cosmos, the overwhelming probability is that you would find yourself floating inside a cosmic void. Far from any galaxy, far from any star, far from any meaningful source of warmth. In such a place, the temperature environment would be dominated almost entirely by the faint glow of the cosmic microwave background. About 2.7 Kelvin, almost absolute zero. This realization leads to a profound shift in perspective. The warm places in the universe, the regions where stars burn and planets orbit, are incredibly rare. They occupy an almost negligible fraction of cosmic volume. Even within galaxies, most of the space between stars remains extremely cold. A star like our Sun may heat the surfaces of nearby planets and warm the surrounding dust and gas. But that influence fades quickly with distance. The intensity of radiation from a star follows a rule known as the inverse square law. If you double your distance from a light source, the intensity drops to 1/4. Triple the distance, and the intensity falls to 1/9. By the time you move just a few light-years away from a star, its radiation becomes extremely weak. This means that the sphere of space meaningfully warmed by any given star is tiny compared to the vast emptiness separating stellar systems. Even our Sun, an enormous thermonuclear furnace producing unimaginable amounts of energy, only warms a thin shell of space around itself. Earth lies inside that shell. But the region where liquid water can exist on a planet's surface, the so-called habitable zone, is remarkably narrow. Move slightly closer to the Sun and oceans would begin to evaporate. Move slightly farther away and the oceans would freeze solid. The comfortable warmth of Earth occupies an extremely small region within the solar system. And the solar system itself is an almost microscopic dot within the galaxy. The galaxy is a tiny island within a much larger cosmic ocean, and that ocean is overwhelmingly cold. In fact, if you were to measure the total volume of the observable universe and compare it to the volume occupied by stars themselves, the difference would be almost impossible to comprehend. Stars account for less than 1/trillionth of the universe's total volume. Practically speaking, they are statistical specks. Everything else is darkness. Everything else is emptiness. Everything else hovers only a few degrees above absolute zero. The cold is not simply present in the universe, it dominates it. The glowing structures we see through telescopes, spiral galaxies, star clusters, brilliant nebulae, are like sparks in an endless night. Beautiful, powerful, but incredibly rare. And this imbalance becomes even more dramatic when we consider not only the space of the universe, but also its history. Because the universe was not always cold. In fact, it began as one of the hottest environments imaginable. The cosmic microwave background we discussed earlier is only the faint remnant of that ancient heat, the leftover glow of a time when the entire universe was hotter than the core of any star that exists today. To understand how the cosmos cooled from that fiery beginning to the frozen darkness we see now, we must look at the thermal history of the universe itself. A story that begins with the Big Bang, and a temperature so extreme that even the laws of physics struggle to describe it. Long before the universe became the cold, dark place we see today, it was something entirely different. It began in heat. Unimaginable heat. Nearly 13.8 billion years ago, the universe emerged from an event we call the Big Bang. Despite the name, the Big Bang was not an explosion in space. It was an expansion of space itself. In the earliest instant, the entire observable universe existed in a state of extreme density and temperature. Every particle of matter, every photon of radiation, everything that would one day become galaxies, stars, planets, oceans, and living creatures was compressed into a tiny, intensely energetic state. The temperatures during these earliest moments were so high that ordinary matter could not exist. Atoms could not form. Atomic nuclei could not even remain stable. The universe was a seething ocean of fundamental particles, quarks, electrons, photons, neutrinos, all colliding and interacting with unimaginable energy. During the first fractions of a second, the temperature exceeded trillions of degrees. At those energies, the forces of nature behave differently than they do today. Physics itself enters a realm that scientists are still trying to fully understand. But as dramatic as those conditions were, they did not last long. Because from the very beginning, the universe was expanding. And expansion causes cooling. Imagine a gas trapped inside a container. If the container suddenly grows larger, the gas spreads out. The particles collide less frequently, their energy spreads across a larger volume, and the temperature drops. Something very similar happened to the universe itself. As space expanded, the energy of radiation stretched across a growing cosmic volume. Particle collisions became less frequent. The average energy of matter and radiation gradually declined. Within the first second after the Big Bang, the temperature had already dropped from trillions of degrees to around 10 billion Kelvin. Still unimaginably hot, but far cooler than the first instant of creation. As the universe continued expanding, the cooling allowed new structures to form. About 3 minutes after the Big Bang, the universe had cooled enough for protons and neutrons to begin combining into the first atomic nuclei. This process is known as Big Bang nucleosynthesis. Hydrogen nuclei formed first. Some of those protons combined with neutrons to create deuterium, a heavy form of hydrogen. Other reactions produced helium nuclei, consisting of 2 protons and 2 neutrons. Tiny traces of lithium also formed, but heavier elements could not yet exist. The universe cooled too quickly for complex nuclear reactions to continue. Within about 20 minutes, nucleosynthesis largely ended. The chemical composition of the universe was set. Roughly 75% hydrogen, about 25% helium, and tiny traces of lithium. Everything else, the carbon in your body, the oxygen you breathe, the iron in your blood, would come much later, forged inside stars. But at this early stage, even though nuclei had formed, atoms still could not exist. Electrons were still too energetic to remain attached to atomic nuclei. Every time an electron tried to bind with a proton, high-energy photons would immediately knock it free again. The universe remained a hot plasma, a glowing fog of charged particles and radiation. Photons constantly scattered off electrons, bouncing randomly in every direction. Light could not travel freely. The universe was opaque. If an observer could somehow have existed at that time, they would not have seen distant objects. Every direction would appear as a blinding wall of glowing plasma. This state persisted for hundreds of thousands of years. During that time, the universe continued expanding and cooling. Gradually, the average energy of particles dropped lower and lower. Finally, around 380,000 years after the Big Bang, the temperature reached a critical threshold, about 3,000 Kelvin. At this point, electrons slowed down enough to remain bound to atomic nuclei. Hydrogen atoms formed, helium atoms formed. For the first time in cosmic history, matter became electrically neutral. This moment is known as recombination, and it changed the universe forever. Without free electrons constantly scattering photons, light could suddenly travel through space without being interrupted. The fog cleared. Radiation that had previously been trapped within the plasma began streaming freely across the cosmos. Those photons spread outward in every direction, and they are still traveling today. What we observe as the cosmic microwave background is the relic radiation released at that moment when the universe became transparent. But the story does not end there, because the universe did not stop expanding. As space continued stretching, the wavelengths of those ancient photons stretched along with it. Longer wavelengths mean lower energy. Lower energy means lower temperature. Over billions of years, the radiation cooled from 3,000 Kelvin down to just 2.725 Kelvin today. That faint glow still fills the entire universe. It is the afterimage of creation itself. But something else happened as the universe cooled. Gravity began to shape the cosmos. Tiny variations in density, regions where matter was slightly more concentrated than average, started pulling surrounding material toward them. These small fluctuations slowly grew. Gas clouds collapsed, matter clumped together. Over millions and then billions of years, gravity sculpted the universe into the structures we see today. Galaxies formed, stars ignited, planets assembled from disks of gas and dust surrounding newborn suns. In these rare pockets of cosmic structure, temperatures rose again. Inside the cores of stars, nuclear fusion began producing enormous amounts of heat. Stars became furnaces, converting hydrogen into helium and releasing energy that illuminated the surrounding darkness. For the first time since the early universe, localized regions of intense heat returned. But these warm regions remained tiny compared to the vast cold spaces between them. The overall trend of the universe never changed. Expansion continued, cooling continued. Even today, the universe is still expanding. Galaxies are drifting farther apart. The wavelengths of cosmic radiation continue stretching. And the temperature of the cosmic microwave background continues to decline, very slowly, but steadily. In billions of years, the background temperature will fall below 2 Kelvin. In trillions of years, it will drop even further. The universe is slowly cooling toward an ultimate state of extreme cold. And that future brings us to one final idea, perhaps the most haunting one of all. If the universe continues expanding forever, if stars eventually exhaust their fuel, if galaxies grow dark and the background radiation fades further and further, then the cosmos may be heading towards something scientists call heat death, a future where almost no usable energy remains. A universe of fading stars, cooling remnants, and endless darkness. To understand that distant fate and what it means for the warmth we experience today, we must look ahead to the long-term future of the cosmos, a future where the cold may finally become absolute. If we step back and look at the universe across its entire history, a clear pattern emerges. It began in overwhelming heat. It has been cooling ever since. And if the laws of physics continue to behave the way we understand them today, that cooling will never truly stop. The universe is slowly drifting toward a future of deeper and deeper cold. This idea is known as the heat death of the universe. Despite the dramatic name, heat death does not mean that the universe will suddenly freeze in some catastrophic event. It is not an explosion, a collapse, or a violent transformation. Instead, it is the quiet end of usable energy. To understand what that means, we need to think again about something we discussed earlier. Heat flows from regions of higher energy to regions of lower energy. A hot object placed next to a cooler one will gradually transfer energy until both reach the same temperature. This process continues everywhere in nature. Warm coffee cools to room temperature. Ice melts in a warm room. A heated metal rod eventually becomes the same temperature as its surroundings. In every case, energy spreads out. Physicists describe this tendency using the concept of entropy. Entropy measures how evenly energy is distributed within a system. When energy is concentrated in one place, like the hot core of a star, entropy is relatively low. There is still usable energy available to do work. But as energy spreads out and temperatures equalize, entropy increases. Eventually, the system reaches a state where energy is evenly distributed everywhere. At that point, nothing interesting can happen. No heat flows. No work can be extracted. Everything simply sits in thermal equilibrium. The universe, taken as a whole, appears to be moving steadily towards such a state. Today, stars are the engines that keep the cosmos interesting. Inside the cores of stars, nuclear fusion converts hydrogen into helium, releasing enormous amounts of energy. This energy radiates outward into space, warming nearby planets and lighting the darkness between galaxies. Our sun alone converts roughly 4 million tons of mass into energy every second. Across the universe, trillions of stars are performing similar reactions. But this process cannot continue forever. Stars run on fuel. Hydrogen inside their cores gradually becomes depleted as fusion continues. Eventually, the fuel runs low and the star begins to change. Small stars like our sun expand into red giants, shedding their outer layers before collapsing into dense remnants known as white dwarfs. More massive stars end their lives in spectacular supernova explosions, leaving behind neutron stars or black holes. These stellar remnants remain extremely hot at first, but they no longer produce new energy through fusion. Instead, they slowly radiate away the heat they already possess. Over billions and trillions of years, they cool. White dwarfs gradually fade into black dwarfs, hypothetical objects that emit almost no light or heat. Neutron stars lose their energy through radiation and particle emission. Even black holes, once thought to be eternal, are predicted to slowly evaporate through a process known as Hawking radiation. This evaporation is incredibly slow. A black hole with the mass of our sun would take about 10 to the power of 67 years to disappear completely. Supermassive black holes, the giants lurking at the centers of galaxies, could survive for 10 to the power of 100 years or longer. These numbers are so enormous that they almost defy comprehension. For comparison, the current age of the universe is only about 13.8 billion years. Yet even these titanic objects are not permanent. Given enough time, they too will fade away. As the universe ages, fewer and fewer stars will exist. Star formation will gradually slow as galaxies consume the gas needed to create new suns. Eventually, billions of years in the future, the era of star formation will end entirely. No new stars will ignite. Existing stars will continue burning for trillions of years, but eventually even the longest-lived red dwarfs will exhaust their fuel. The sky will grow darker. Galaxies will fill with stellar remnants, white dwarfs, neutron stars, and black holes drifting silently through space. Over unimaginable spans of time, gravitational interactions will scatter many of these objects out of their galaxies entirely. Galaxies themselves may slowly dissolve. Meanwhile, the universe continues expanding. Galaxies drift farther apart. Radiation stretches to longer and longer wavelengths. The temperature of the cosmic microwave background continues to fall. The universe becomes colder, darker, more dilute. Eventually, trillions upon trillions of years in the future, the cosmos may reach a state where almost all matter exists as cold remnants drifting through an ever-expanding void. The temperature of space will approach absolute zero more closely than ever before. Not because something forced the universe to freeze, but because energy has spread so evenly that no region remains significantly warmer than another. This is heat death, a universe where temperature differences, the driving force behind all physical processes, have nearly vanished. Without temperature differences, engines cannot run. Stars cannot shine. Chemical reactions slow to a halt. Complex structures become increasingly rare. The cosmos settles into a quiet equilibrium. Yet when we consider this distant future, something remarkable becomes clear. We are living in an extremely unusual moment in cosmic history. The universe is still young enough for stars to shine, still energetic enough for galaxies to form, still warm enough in certain regions for planets like Earth to host liquid water. Life, as far as we know, depends on temperature differences. Energy flowing from a hot source to a cooler environment allows biological systems to perform work, build complex molecules, and sustain metabolism. On Earth, nearly all life ultimately depends on the energy of the sun. Our planet sits at a distance where sunlight warms the surface enough to maintain oceans of liquid water, but not so much that everything boils away. This delicate balance is rare. Too close to a star and a planet becomes a scorching desert like Venus. Too far away and it freezes into an icy world like Europa or Pluto. The narrow region where temperatures allow liquid water to exist is called the habitable zone. Earth happens to lie within that thin band, protected by its atmosphere, stabilized by its magnetic field, and warmed by a star that has burned steadily for billions of years. From a cosmic perspective, this combination of circumstances is extraordinary. Most of the universe is not like this. Most of the universe is dark, empty space hovering only a few degrees above absolute zero. Stars are rare. Habitable planets are rarer still. The warmth that surrounds us on Earth, the gentle temperature that allows oceans, weather, forests, and life itself to exist, is not the default state of the cosmos. It is an exception. A tiny pocket of warmth within an overwhelmingly cold universe. Every sunrise that warms the surface of this planet is a reminder of that unlikely balance. Every breath of warm air on a cool morning is a quiet defiance of the cosmic background. Because while the universe may ultimately drift toward deeper cold, we exist during the brief era when warmth still shines in scattered islands across the darkness. And one of those islands happens to be here, on a small world orbiting an ordinary star in a quiet corner of the Milky Way. A place where, against all odds, the cold of the universe has not yet won. At least, not yet. If the cosmos keeps you wondering, subscribe to Cosmos Before Us, and let the universe guide you to sleep.